Okay, is it visible for you?
Yes, sir.
Yeah. So module 3, 4, module 4, we had studied about design of permanent joints, which includes riveted and welded joints. Okay. So we started off with welded joints. So as we know, welding is a process of joining two similar or dissimilar metals by heating to a suitable temperature, that is almost to the melting temperature, with or without the application of pressure. Okay, that is the definition of welded joints or welding as a process. The basic types of welded joints are lap joint and butt joint. So in case of lap joint, the components or metals to be fastened will be overlapping with each other, something like this. In butt joint, the metals that are to be welded will be butt against each other, and then welding is done along the joint. Of course, before doing the welding, a small preparation needs to be made in the metal pieces. Okay, this is what was called as lap joint and butt joint. Then we again now gone through some types of welded joints. So basically this is the butt joint. This is what I was telling about preparation of the metal. That is, we are going to do some cleaning operation and filing at an angle before we go for welding in case of butt joint. Whereas in lap joint, we straight away mount one above the other, the metals to be joined, and then welding is carried out. Depending upon the application, you will have welding on two sides or on one side. Okay. And other joints, what we have is T joint, corner joint, edge joint, and so forth. So these are all some of the types of welded joints. Now, coming to lap joints. So lap joints, we should get a picture into your mind that the metals to be joined will be overlapped with each other, something like this. So in this lap joint, we can further classify them as transverse fillet weld and parallel fillet welds. So let's look at what is parallel fillet weld. So parallel fillet welds are the welds that are done which are parallel to the axis of loading, right? The welds which are parallel to the axis of loading are called parallel fillet welds. Are you with me? Are you with me? Okay.
Yes, sir.
Yeah. Next, we learn about transverse fillet weld. Transverse, as the name itself indicates, that transverse is nothing but the direction which is perpendicular to the axis of loading. That is what is called as transverse loading. So when we talk about transverse fillet weld, the welds which are done which perpendicular to the axis of loading, such type of welds are called transverse fillet welds. Okay, that is, when the welds are parallel to the axis of loading, then we call them as parallel fillet welds. Welds which are perpendicular to the axis of loading, they are called transverse fillet welds. So these are the type of lap joints. Okay, you will have lap parallel fillet weld and transverse fillet weld. Then, coming to the cross section of the weld, it is considered to be a right angle triangle. Okay, this is denoted as throat of the weld, and this is the size of the weld, that is LS. Okay. Next, parallel fillet welds are subjected to shear stress because you will have metals placed one above the other. As the load is applied, there is going to be the metals will going to shear along the plane of joint, that is along the plane of this joint, that is along this plane. Okay, there is going to be stress. So such type of stress which act along the plane are called shear stresses, right? So the shear stress tau is given by P by area of contact, that is nothing but throat into length of parallel fillet weld. Okay, throat, as we know, this is the throat. Okay, this is the throat of the weld. That multiplied by length will give you the length, the area of the weld that is done, right? So therefore, the parallel fillet welds are subjected to shear stress given by P by A. P is the applied load. Area of the weld is nothing but length of the weld multiplied by throat of the weld. That will give you the area of the weld. Okay, and this area, this throat is nothing but 0.707 times the weld size. That is what we learn here. It is 0.70 times, okay, weld size. So therefore the throat is replaced by 0.707 times W. Length of parallel fillet weld remains as it is. So finally, if I want to calculate shear load, so just cross multiply, we are going to get the shear load to be given by 0.707 times weld size multiplied by length of parallel fillet weld multiplied by shear stress, okay, shear stress of the joint or the material, right? So that is about shear load. Then the transverse fillet welds are subjected to normal load. So we have understood what is transverse fillet weld. It is the weld that is done perpendicular to the axis of loading is called transverse fillet weld. So the length of transverse fillet weld we can denote it by Ln. Again, the normal stress sigma is given by load by area of cross section. So load P remains as it is, and then area of the weld remains as throat into length of transverse fillet weld. Again, throat is replaced by 0.707 times W into Ln. So if I want load because of normal weld, I want, so then cross multiply, I am going to get length, load because of normal weld or transverse fillet weld is given by 0.707 times W into length of transverse fillet weld into normal stress. So one is P shear, another is P normal. P shear we are going to get when we have parallel fillet weld. P normal we are going to get when we have transverse fillet weld. Are you with me? Are you with me?
Yes,
Yes.
sir.
Yes, sir.
Yeah. Suppose if you have a joint which consists of both parallel fillet weld and transverse fillet weld, then the total load P will be shared. Okay, total load P will be equal to P because of shear plus P because of normal or transverse fillet weld. Okay, I think that's what we have taken next. Yeah. That is compound fillet weld will have parallel fillet weld as well as transverse fillet weld. When you have such welded joints, all right, when we have such compound fillet welded joints, we will have total load P will be equal to P normal plus P shear. So bring the equations from the previous slide over here, whatever that we have learned, bring those equations. We are going to have P normal, this is the load P normal, this is load because P shear, right? So put together the total load is shared between the parallel fillet weld and transverse fillet weld. And now, one more important thing here is, whenever we have got free ends of the weld, we need to add 5 mm to the length of the weld at each free end. In this case, in the compound fillet weld, we have 2 free ends. So 5 into 2 free ends plus the length that we have calculated will give you the total length of the weld. So if you have 4 number of free ends, 5 I will be 4. So 5, that is in total we are going to add 20 mm for the effective length to get total length of the weld. This we are going to do to take care of what? To take care of what? To take care of, yeah?
Ineffective or incomplete fusion.
Ineffective or incomplete fusion during welding. That is, if by operator mistake or a fixture mistake, there can be so many mistakes. So to overcome those things, okay, we'll have more length of the weld compared to effective length, okay, to take care of ineffective fusion or incomplete fusion. Is that okay? Are you with me?
Yes, sir.
Yeah. So next what we did is,
Sir, I had a doubt.
Yeah.
In the previous slide,
Yeah.
so while taking LP, we have to take 5 into 2, and then again for LT, we have to take the
No, no,
remaining
no.
3.
When we are asked to calculate the total length of the weld, okay, total length of the weld when we are asked to calculate, so we are going to find out LP or LN, whatever that's asked, we are going to find out, and then for that effective length, we are going to add 5 mm later. That we'll see in the problem. You will understand it now, okay?
Okay, sir.
Yeah. So coming to a problem, we have taken a problem wherein a structural plate and which is 10 mm thick is welded by parallel fillet weld to carry a load of 20 kilonewton. Okay, and he has asked you to determine the length of each weld for both static and dynamic loading condition. Right now, so shear stress is not to exceed 60 megapascal is what he has given you. So B is 100 mm, welds at the metal thickness is given is 10 mm, load carried is 20,000 Newton, shear stress is 60 megapascal. So for static loading, so we know tau is equal to P by area of cross section, that is nothing but throat into length of parallel fillet weld. This throat is replaced by 0.707 WO into length of parallel fillet weld. Now here, shear stress is known, load carried is known, weld size is known. So we have calculated length of parallel fillet weld. This is the total length, effective length of the parallel fillet weld. When you have to calculate total length of the weld, here if you look at, we have how many free ends now? How many free ends we have?
4.
4 free ends. So that's why here I have had taken 5 into 4 number of free ends. So for 47 mm, we have added another 20 mm to get the effective total length of the parallel fillet welded joint. I hope this will answer your question, Chinmay.
Yes, sir.
Okay, got it, no?
Yes,
Yeah.
sir.
Next, for dynamic loading condition, what we need to do is we need to take stress concentration factor. For that, we need to refer table 6.3 in page number 94. Page number 94 of your data handbook. So the stress concentration factor, we have learned that it is the ratio of maximum stress to allowable stress. So in this case, it's going to be shear stress. And from the table 6.3, we are given with K sigma to be equal to 2.7 for parallel or longitudinal fillet weld. So what it does is the allowable stress will come down by K sigma times. That is 60 divided by 2.7, the shear stress value will be reduced because of stress concentration factor of 2.7. So what will happen when my stress is less, my length of weld that is to be done will go up. So therefore, again use the same equation, but instead of in the previous static condition, we had used the 60 megapascal as shear stress, whereas when we have to consider dynamic loading effect, we have taken the stress concentration factor into effect, which will reduce the shear stress allowable. So using that, we calculate length of the weld. Again, for that length, effective length, we are going to add 5 times the free end to get total length of the weld. Is that okay? Is that okay? When the joint is subjected to dynamic loading, length of weld required is 147 mm. Whereas when it is subjected to static loading, length of weld was found to be how much? 57 mm. Correct? Correct?
Yes,
Rather
sir.
67, right? I should go back, right? So length of weld was 67 mm for static loading condition. When you have to use the same joint for dynamic condition, the length of the weld will be 147 mm. Okay, got the difference between static and dynamic loading conditions? Did you get
Yes,
that?
sir. Yes, sir.
Yeah, anybody? Any doubt? Any doubt? Is anyone?
Sir,
Okay,
could you explain once again, please?
which one?
Sir, that the different lengths of the in dynamic and static loading, that part.
Yeah. So when we are, yeah. So in case of static loading condition, okay, so the shear stress is given by load by area of cross section. So the shear stress given in the problem is 60 megapascal. So we use the 60 megapascal as the reference shear stress, and we calculated length of parallel fillet weld. And for this, since in a parallel fillet weld we have 4 free ends, so multiply those 4 free ends over here. This is third, and this is 4 free ends. So 5 into 4 will be added. That is 20 mm will be added to the effective length that we have calculated over here. So that will give us 67.14 mm to be the total length of the weld. Whereas when you subject the same joint for dynamic loading condition, we need to consider the stress concentration factor K sigma, okay, which will reduce the maximum shear stress of 60 megapascal to 22.2. So if you want to get the value of K sigma, you should refer to the table 6.3 in page number 94 of your data handbook. So that will make, when I consider the stress concentration factor, the allowable shear stress will be less than whatever that is given over there because of stress concentration factor 2.7. So the allowable shear stress will be 22.2. That is, we are going to find out length of the weld based on shear stress of 22.2. Whereas in case of static loading, the length of weld was calculated based on shear stress of 60 megapascal. Whereas in this case, in dynamic loading condition, length of weld will be calculated with reference to 22.2 shear stress. Okay, so which will give us effective length to be equal to 127.3 millimeter. And again 4 free ends are there. To that 127, I have added 5 into 420, which will give us 147 mm as the total length of the weld. So to take care of dynamic action, length of weld is more compared to static loading, where statically loaded welded joint, which is 67.14. Is that okay? Got it, Sautrik Rai?
Yes, sir. Yes, sir. So just one more doubt, sir.
Yeah,
Sir, over here in the figure, sir, you have circled the end points of the
yeah,
welding, sir.
yeah,
Sir, is there any condition that, like, not condition, sir, in any, yes, sir, any kind of loading, sir, where we will
mm,
take, like in the below figure, sir, we will take the, for the value of I, we will take
yeah.
the bottom part and top part, we'll consider the bottom part and top part as
No, no,
sides.
this is only top view of this. This is the top view of this joint. This I consider it as front view of the same joint. This is the top view of the same joint. Okay. I mean,
Okay,
rather
sir.
this can be the front view and that is the top view. I would say that. Okay. So the below one is the front view and top one is the top view. Okay. So this front view, this is top view I take. So here you put yourself to be a welder or here. You take your welding rod and start here, correct? You start here. So there may be chance that you will skip the weld there. There can be incomplete fusion at the beginning. Okay. And as you travel forward, maybe at this end again, there may be some incomplete fusion, right? So therefore, you have 2 free ends over there, which may have potentially incomplete fusion zones. Okay, are you with me?
Yes, sir. Yes, sir.
And similarly, the other weld over here. So therefore, there are 4 points where there can be incomplete fusion of the weld. So therefore, we take 4 free ends and add to the effective length, we'll get the total length of the weld. Is that okay?
Yes, sir. Yes.
Yeah. So this is about the static and dynamic loading of the joint. Again, we took up a problem wherein we have compound fillet weld and this is the value of B. P is the applied load. Okay. And then as we have learned in the previous somewhere here, P will be, that is total load is shared between normal and shear loads. So that is the same thing that we have taken over here. Total load P will be equal to load shared because of normal, transverse fillet weld, and load shared because of parallel fillet weld. Again, we found out length of parallel fillet weld for dynamic loading as well as static loading conditions. Okay. So that was about axially loaded welded joints. Next, what we took was the eccentrically loaded welded joints. Are you all there with me? Okay. So in eccentrically loaded welded joints, load is applied at a distance E. Okay. That is eccentric distance from center of gravity of the weld. So the parallel fillet weld length is taken as N, transverse fillet weld length is taken as M, and this is the center of gravity we are going to find out. Distance of center of gravity from transverse fillet weld is taken as Ny. Okay, Ny, and the remaining distance in parallel fillet weld is taken as N1, or is the radius of the joint from with reference to CG, and theta is the angle. These are the terminologies. So the value of Ny, we can get it from the table in the data handbook. Okay. So what will happen? In structural joints, the externally applied force will not pass through the geometric center. Such joints are called eccentrically loaded welded joints. Whereas in the previous case, the loading was passing through the center of gravity, whereas in this case, the load will be acting away from line of center of gravity or geometric center. That's why they are called eccentrically loaded welded joints. Next, we took the design procedure for the eccentrically loaded welded joints. First step we found was the total length of the weld. Second step is to find direct load per unit length, that is nothing but load divided by total length of the weld. Then locate CG, that is, as I said, find out Ny. Refer table 6.7 in page number 96. Okay, and we can find out the value of Ny. Once I find the value of Ny, I can find the value of N1 from N. N minus Ny will give me the value of N1. Okay, once I know the value of N1, okay, that is this value, I know N1. So radius will be equal to N1 under root N1 plus, N1 square from Pythagoras theorem, R will be equal to N1 square plus M by 2. This distance will be M by 2, correct? Are you with me? This distance is M by 2. So therefore, what I am going to get here is M by 2 whole square. That will give me the value of R here. Are you with me? Are you with me? Yeah?
Yes, sir.
Yes, sir. Fine. And find out eccentricity from the given figure, and then find out cos theta. Then find out polar moment of inertia in torsion. Use the same table 6.7, page number 96. Ignore, this is an important one, ignore HT value while calculating JW. Okay, at this moment. Then twisting moment per unit length, PER by JW is what we calculate. Then find out resultant load, and from shear stress equation, we can find the size of the weld. Any doubt in this? I will take up a problem for that, right? So we have found out the size, determine the size of the weld required for a flat plate to a steel column loaded as shown in figure. Permissible shear stress for the weld material is 70 MPa. Okay, so this is the figure that we have given. This is the value of M, correct? And this is the value of N. So N is equal to 200, M is equal to 300. This distance is 500. Remember, be careful. Eccentricity is the distance between CG to the point of application of load. This is eccentricity, not 500. Okay, you have to find out eccentricity, right? To find out eccentricity, we need to find out CG. So just follow the procedure. So we have taken M equal to 300, N as 200, load applied is 60 kilonewton given in the problem, and shear stress of the weld material is 70 megapascal given in the problem. So first step is to find total length of the weld, that is 200 plus 300 plus again 200 over here, right? So put together is 700. Then find out direct load per unit length, P by L. So P is known, the total length is known, we found a direct length. Then locate NY. NY from data handbook, it is given by N square by 2N plus M. So find out NY, that is from CG, this distance is NY. So N minus NY will give us what? N minus NY will give us the value of N1. Once I know the value of N1, I can find the value of R, correct? I can find the value of R. Then eccentricity will be 500, in this case 500 plus N1. This is N1, correct? This is N1. Okay? 500 plus N1 will give us the value of eccentricity, which is 642.9 in this case. Then cos theta is equal to N1 by adjacent by hypotenuse. So you will get the value of cos theta, and then find out JW, and then find out resultant load, then get the weld size. That's all we need to do. Is that okay? Is that fine?
Sir, Pn, that's a formula, sir.
Yeah.
Pn.
P into E into R by JW. Load, eccentricity, radius of the weld. Okay?
So
Next.
size of the weld means what all parameters should we find?
Which one?
In the question it says size of the weld.
Yeah, it is W. W only is
Find
what.
W. Okay.
Yeah.
Okay.
Yeah. So we solved another several problems. Only variation with this problem is that we need to find out mx separately. Okay. So from table 6.7, find out mx, then find out ny. Both that we have to use while calculating the value of radius of the weld. Okay. You have to be careful when you have that problem like this, the welded joint like this, where you have to find out mx and also you have to find out n1. Both you have to find out for you to calculate the radius of the weld. Is that okay? Fine. So this is what we did, and we solved few problems. Again, another set of problems we solved wherein he will give you the type of welded joint, and we need to refer table 6.1 in page number 93 of your data handbook. We need to refer, take care of that figure, that is identify the figure that is given, use the equation that is given in the data handbook, and then calculate the required parameter, maybe it is stress or load or whatever, right? So we need to calculate the given parameter by identifying proper figure from table 6.1 page number 93. So here he has given you a circular rod which is welded to a plate subjected to a bending moment. Okay. So for that the equation is given as 5.66 bending moment divided by pi into h into d square. He will give you what is that h in the figure itself. There's nothing but fillet weld h. So it is given as 10 mm over here, HRW. They are one and the same. So 10 mm that's given in the problem. Substitute, get the parameter. Okay. Similarly, the challenge lies in identifying correct figure from table 6.1 of page number 93. That's it. Okay. And then we went to eccentric loading of welded joints type 2. So again, in type 2, we are given with welded joint something like this. Okay. So I channel, C channel, and so on, which are welded at multiple locations. So when we have such a type of eccentric loaded welded joints, so we need to follow the again design procedure, total length of the weld, direct load, and here you have to find out ZW for both top and bottom and choose a smaller value from table 6.7 page number 97. Then find out normal load, resultant load, and shear stress equal to resultant load by area. That should give you the weld size. Okay. So again here from table 6.7, it is our job to identify the proper type of welded joint that is required for a bracket. So here we need to determine the size of the weld for a bracket as shown, loaded as shown. Allowable shear stress in the weld is 75 megapascal. So find out total length will be this plus this plus this plus this. Put together is the total length of the weld. Eccentricity is given as 960 megapascal over here. I mean 960 mm. Okay. And find out ZW for top and bottom, and then find out the remaining parameters. This is another type of welded joint that we learned. So here when you have circular cross-section welded joint, ZW will be pi m square by 4. That's one thing. To get length of the weld, total length of the weld is given by circumference of the circle, that is nothing but 2 pi r or pi d. That should give you total length of the weld. That's the only change from the previous problems. Any doubt, anybody in this? Any doubt? So we have gone through welded joints, correct? So welded joints, we have axially loaded member, eccentrically loaded member. So axially loaded, parallel and transverse fillet welds. Eccentrically loaded, we have a design procedure. Then another eccentrically loaded welded joints type 2, identify correct figure from table 6.7, use the equation and find out ZW top and bottom, choose a smaller value. These are the things that we did in welded joints. Are you all with me? Are you all with me?
Yes, sir.
Yeah. Now we will go to a recap of
Yes, sir.
welded joints. Yeah. The screen has come for riveted joints for you people.
Yes, sir.
Yeah. All right. So again, so welded joints is one of the permanent type joints. Riveted joints is also another type of permanent joints. So riveting is a popular method of fastening or joining metal plates. Advantages: rate of production is high, low cost, simple, dependable, unskilled labor can be employed. Disadvantages: it cannot be dismantled unless otherwise we dismantle. It cannot be held back. Then joints are not comfortable for airtight and watertight, and protruding rivets are undesirable in food processing industries. Majorly, the application of riveted joints are in low pressure containers, ship hulls, boilers. This is a major place where riveted joints are used, and aerostructure, again, that's a major one. Again, bridges, again, a major application of riveted joints. So what this rivet material is made of is that basically wrought iron or copper or aluminum alloys are used. Now there are plenty of other types of materials that are used for riveted joints. Again, in riveted joints we have got lap joint and butt joint. Okay, so these are some of the examples. This was the bridge construction over there. Okay, then ship hulls where we have riveted joints. Then aerostructure, again we have got riveted joints over here, and then yeah, coming to lap joints. Again, lap joints are what? Metal pieces to be fastened or held or overlap with each other. That is what is called as lap joint. So when you have two metal pieces overlapping with each other and you have one row of riveted joints, then it is called single riveted lap joint. When you have two rows, it is double riveted lap joint. And when the pitch is in line, then we call it as chain riveting. When you have the pitch of the rivets in zigzag manner, that is a location of rivets in zigzag manner, then we call such riveted joints as zigzag riveting. Any doubt, anybody? Okay, next. This is again chain riveting. What is the type of joint here? What is this joint called?
Lap joint.
Lap joint, one thing. Next. There are three characteristics that you can tell about this. What are they?
Chain riveted.
Okay. Lap joint. Third one is?
Three rows of
Yeah, that is triple riveted lap joint with chain riveting. Is that okay? Are you there?
Yes, sir.
Here what is this called? Double riveted lap joint with chain riveting. Then what is this called?
Zigzag.
triple riveted zigzag.
Yeah, lap joint. Okay? Okay, na? Next, I'll come to butt joint, right? Butting is the materials that are to be fastened will be butt against each other like this. And if you want to join these two metal pieces, we need to have cover plate 1, cover plate 2. Sometimes only one cover plate is used. Most of the applications, double cover plate is used, and the width of cover plate will be taken as equal if nothing is specified. So we'll have one cover plate on top, a cover plate on bottom, and all the three components will be drilled, okay, and then riveting operation is going to be carried out. Is it okay? So you will have this one is a double riveted, double strap butt joint. You should not get confused with 1, 2, 3, 4. Why is called double riveted? We need to consider only the joint of one plate, not both the plates at a time. So when you take that, so we have got two rows of rivets over here. Okay, so therefore it is double riveted, double strap, because this is strap 1, strap 2. They call both strap or cover as same. Okay, covers or straps, they are one and the same. Okay, so double strap, chain, butt joint. Is that okay? Now coming to the failure of riveted joints. In what all ways the failure of riveted joints can occur? That is what we are trying to understand. Once we understand that, it will be easy for us to do the designing part. Okay, so therefore it's important to understand as to how the components would fail. Based on that, we can do the design process. So when you come to failure of riveted joints, it can fail because of crushing of rivets. It can fail because of tearing of plates. This is crushing, this is tearing, and third one is shearing of rivets. What are they? Can someone read again? What are the three types of rivets may fail? Three ways of rivet failure.
Crushing of rivets, tearing of rivets,
Shearing of rivets. Next, we'll come to what is shearing of rivets in detail. Okay, can anyone explain what I intend to explain over here? What can be explained over here? Can anyone take up?
Due to the axial forces that are acting,
Little louder, little louder.
due to the actual forces that are acting on uh, the two pieces that are to be butt, there's a shearing force that will separate the that will tear the rivet apart.
Mm, next, one more. Tarun, are you there?
So, so due to the forces subjected to the rivet joint,
Hmm.
the shearing plane comes into existence since uh, the rivet is butt against each other.
Hmm.
So it might happen in two ways. If we have single cover, then only one plane of shear might come into existence,
Hmm.
and we have two covers, we'll have uh, uh, two shear planes basically.
Hmm. That's one. Next, Jain Bansali, are you there? Jain,
Yes, sir.
can you explain what I meant to say? We are discussing about failure of riveted joints. So what I intend to explain here is
Sir, in riveted joints, I would go with confirm because there are two in double butt joints. There are like two shearing planes.
hmm,
So there will be application of force from two different sides, and the butt joint will break from middle. So there
hmm.
will be two different. Uh,
No, there is a specific name for that. So I just explain. I'm
Single
expecting
shear and
that.
double shear.
Yeah.
Single shear and double shear.
Yeah, that's what I was expecting from you people. Okay. So shearing can happen because of two ways. One is single shear, another is what, Chinmay?
Double shear.
Double shear. Okay. Pranay Elmule Pati, are you there?
Yes, sir.
Can you explain what is single shear, what is double shear? Now.
In a single shear, a material is subjected to shearing only in one plane, while in
Correct.
double shear, it's subject to shear in two planes.
Okay. So which is in double shear in these three figures?
In the first figure, it's a single shear, and
Okay.
second figure is also a single shear, but the third figure is in double
Double
shear.
shear. Okay, right. So shearing of rivets is one of the ways the rivets can fail, and we have two types. One is single shear, and another is double shear. If the shear plane is only one, then it is the failure is called single shear failure because of single shear. When we have two shear planes, then we call it as double shear. Okay, this can happen in riveted joints. One of the failure types in riveted joints is single shear and double shear. So totally three types of failures: crushing of rivets, tearing of plates, shearing of rivets. Okay, that is sigma C, then sigma T, then sigma S or tau. Please keep that in mind. Now, coming to the design procedure of riveted joints, first we have to find out thickness of the shell depending upon the internal pressure and the diameter of the boiler that is to be designed, and the material's tensile strength, and then joint efficiency. This we can extract from table 5.1 if not given. So first job is to find thickness of the shell, boiler shell, that we need to compute by depending upon internal pressure. It is subjected to the diameter, material tensile strength, and efficiency of the joint. Then important step is to find diameter of the rivet by using Unwin's formula given by equation 5.11. So straight away we can calculate 6.25 times root T and take the standard diameter of rivet from table 5.3b in page number 84. Then, as we know that for carrying out the riveting operation, the plates have to be drilled, correct? We need to make holes in the plates that are to be fastened. So we need to find out hole diameter of the plates. So for that, we have an empirical standard. We need to add 1 mm for diameter of the rivet that we find out here to find out diameter of the rivet hole in the plates. So up to 25 mm, we add 1 mm to the diameter of the rivet. Beyond 25 mm, we add 1.5 mm to the diameter of the rivet. That will give you diameter of the hole in the plate. And for further calculations, we are going to use diameter of the hole, okay, in the plate as the reference. Okay, okay. Then comes pitch of the rivets given by equation so and so, where N1 is number of rivets in a pitch line for single shear, N2 is number of rivets in a pitch line in double shear. So you understood the importance of the single shear and double shear. We cannot calculate the pitch of the rivets if we don't have the clarity of single shear and double shear. Got it now? You people got it?
Yes, sir.
Yeah. Then come to the pitch again using the formula K1T plus 41, which is again an empirical relation. So K1 value we can get from table 5.4a, get the K1 value, again calculate pitch. Note important over here, select minimum value of above two pitches for further calculations. Is that okay? You need to take the minimum of these two for further calculation. Next, what we do, we can find out thickness of core plates, use the equations. Transverse pitch PT is equal to 2 times diameter, length of shank of rivet, sum of thicknesses plus 1.5D, margin is 1.5 times the diameter, then strength of solid plate as if there is no hole present in the plate. So that is strength of solid plate is given by pitch into thickness into tensile strength of the material. Tearing strength is nothing but the effective area. That's it. Say suppose if you have a hole, so you take the effective area over there that by subtracting this area diameter, because there's a hole, there is no material in the hole. So therefore P minus D, instead of P, it is P minus D. That reduce the strength by that much. Okay, and then we find out shearing strength, crushing strength, then find the efficiency using the equation. Any doubt in this? Any doubt?
No, sir.
Fine. One second. Yeah. So just as an example, I'll take over here. Design a double riveted lap joint to cover two plates each 20 mm thick. Allowable stresses in tension, shear, and crushing. One important, very, very important thing that you should understand is, if suppose you get confused with these values, instead it does not specify tension, shear, and compression, don't get panic. So the lowest one will be the shear stress value, highest one will be the crushing strength value, and in between will be the tensile strength value. That you have to keep in mind. Okay. So here we are given with the thickness right away we are given with. So first step we are going to skip, find out the diameter, hole diameter, pitch calculation, length of shank, transverse pitch, margin, strength of solid plate, and so on. Calculate the efficiency. That's all we have to do. Only thing here is, here in the pitch line, okay, while taking single shear, so this is the pitch line that we have taken. In the pitch line, we have half rivet here, half rivet here, half here, and half here. Put together is two rivets which are in single shear. So therefore, N1 is equal to 2. N2, because it's a lap joint, there is no rivets which are in double shear. So N2 is going to be equal to 0. Is that okay? Are you there? Any doubt in this? Again, when you come to a joint like the zigzag joint, in the pitch line, this is the pitch line if we take, okay? In the pitch line, we have half, half, and one full rivet over here, and therefore N1 is equal to 2. Again, it's a lap joint, so therefore there is no rivet which is in double shear, so N2 is going to be 0. Is it okay? So these are all some of the problems that we solved during the process. Again, for boiler joints, it will have both longitudinal and circumferential joint. The longitudinal joint in a boiler is a butt joint because you have a longitudinal, that is along the axis, you will have the riveted joint. So how they do is they take two halves of the cylinders and then join them using a cover plate along the axis. So therefore, it is called a longitudinal joint, which is a butt joint, because these two halves semicircles will butt against each other and then riveting operation is to be done. Circumferential joint is along the circumference of the boiler, the riveting operation is going to be carried out. So therefore, circumferential joint is a lap joint where you have one ring overlapping on the other, and then along the circumference they are going to do the riveting. I have got one more sketch over here, something like this. So you have two semicircular halves butt against each other and riveting is done. This is what? Longitudinal joint, which is a butt joint. So when you have two rings, complete rings, this is one complete ring, this is another complete ring. So these two rings will overlap and along the circumference riveting is done. That's called circumferential joint, which is a lap joint. And remaining things, they all remain same. And diamond joint we learned about recently. And then we learned about eccentrically loaded riveted joints, wherein we are going to have the first we take the CG, then join from CG to center of each of the rivets, draw secondary shear forces, lines perpendicular to the lines L1, L2, L3, L4, and we need to draw direct loads which are parallel to the loading that is subjected to. Then together you have direct load, direct shear load, and secondary shear forces. Angle between them is taken as theta. Important aspect is identifying the heavily loaded rivet. So rivet which is farthest from CG and theta less than 90 degrees is heavily loaded rivet, and only with that reference we need to do further calculations. Is that okay? Are you all there?
Yes, sir.
So could you get the clarity a bit? Could you
Yes,
get the
sir.
clarity a bit?
Yes, sir.
Okay. So that's about riveted joints and welded joints revision part. Monday onwards, we'll start with module 5. That's power screws. Please go through whatever the power screws that we have learned so far. Okay. And because thread terminology and all, again, I'll be going through